Hey, thank you for the introduction and all coming to the right place. Yeah, so I'm at the right place now. It's good. So, okay, it's good to be here. I came here. I was able to come here because I'm doing sabbatical in Berkeley. So I was nearby, and he's just joined. So I asked him, "Can I give a talk?" And he said, "Yes, come." So, and I'm really happy to be here. So today I'm going to talk about gradient method. And if you are familiar with optimization or machine learning, I'm sure you guys all know about gradient method, right? Everyone knows about it, even undergrad students or even high school students these days, right? So I'm going to talk about that. But what's new here? So it's Minimax, not minimization. That's the difference. Okay, so I went to NUIPS 2024, just a month ago. And GAN, I'm sure most of you know about this, right? GAN received the test of the time paper award. And I'm sure everyone will agree that this is deserve this, right? Everyone agrees with this. Because it had a big impact in generative model. It outperformed existing methods, right? So, yes, so I found the talk really interesting. And it changed how we generate the data, right? But also when I look into the conferences, I saw that there's a tutorial on flow matching and invited talk on diffusion stranding of bridges. That's what's happening in the generative model, right? When you learn about generative model these days, if you're new to graduate school, I don't think anyone will, there must be some people doing GAN, that's including me, myself, but most of people are more into this. And diffusion model, now it's commercialized. All use this. And if I look into the papers, it's really hard to find GAN papers. And that's the reality right now. So, and if I ask you why this happened, I'm sure everyone knows the answer if you have taken machine learning. I'm going to get to that by following the introduction slides from the flow matching tutorial. So for those of you who don't know about the generative model, I'll just make it very quick explanation. We want to generate data from this some unknown distribution, where, for example, here is all dogs. We have some data. How you generate it is to start with some noise, Gaussian noise or uniform distribution. You come up with some mapping or transformation that gives you a transformation from one point from this noise distribution to some point in this data distribution, right? That's how it works these days, generative model. How we do it? The first thing that we can come up with is the direct mapping, which corresponds to GAN, right? GAN tries to find this map that when you generate data from here, we want that to decrease the distance from the generated data to the true data. That's how it works. So learning direct map is GAN. So this had an impact. That's why they got the test of time award. But on the other side, if I ask people, have you run GAN? Then they all say, it's really hard to optimize, right? Everyone say that. Hyperparameter tuning, regularization, all those stuff is so difficult. And that comes with this, min-max loss. That's difficult. And when you learn about generative model, that's what we learn. It's bad. So min-max loss is something that you shouldn't do these days, right? So what happened next? Instead of learning direct map, diffusion model, so learning some indirect transformation from here, noise to the real data distribution. So you don't learn direct map, but you learn continuous time process. Either it can be diffusion, jump, or flow matching. Flow matching tries to learn better trajectory, and that was the main point in this slide. So they say something about the faster sampling compared to diffusion, something more, so it has more advantage. So that's why what they were selling this flow matching. I think this is getting more popular. That's why they had the tutorial. So today I'm not going to talk more about the generative model at this point. What I want to try to say here is, I work on optimization. What if this worked well? If min-max loss was not that difficult, what would happen? Will people still use GAN, and commercial products use GAN? Or still diffusion will outperform GAN even if min-max loss is easier to solve? I guess I'm the only one who's thinking about this because I'm working on this. Anyhow, I have a friend who works on diffusion model, and I said, I'm working on GAN, and he said, oh, are you still working on GAN? Yes, I am, right? Anyway, that's the question that I wanted to ask. So I was curious, because I'm in optimization, there's a min-max. For some people, I think, oh, there's nothing much to do here. Because min-max is difficult. But for me, I thought, oh, can I improve something here? Is there a fundamental limit that we cannot do well in the min-max? Is it like are we at the limit, or can we do better? So I'm not really going to say this diffusion model, this will be better or not. That's not the point. My point here is, at some point, other than GAN, we might get into the problem where we need to solve min-max loss. But at that point, are we going to say still, oh, it's not the way to go, and we should do other way? So my question was to get to this. Why am I more interested in min-max loss? Why? So in minimization, in contrast, in minimization or supervised learning, gradient descent works so well, right? So everything works well and everyone uses this. But when it comes to the Minimax, gradient descent-ascent, that seems to be the similar one, doesn't work well. That really seemed odd to me. I know right now, after GAN, 10 years, people have developed a lot of theories and experiments. What they found is still Minimax loss is difficult. And there must be various reasons why this is not working well. But I was curious, what's making this difference? So that's the focus here. And what I'm more specific focus here is, what does gradient descent has? Well, what doesn't GDA doesn't have here? And what I'm trying to focus here is, there is something that is important that was overlooked by the community, and I'm going to talk about this. So I'm going to talk about why GD was able to do better here, but not in GDA. And I'm trying to improve that here. So because of that, I will start talking about reviewing what is known for the GD. Basically, GD converges to local minimizer. That's all everyone knows. But in Minimax, if you get into the details, you will see that we don't have this statement. That's what I'm saying it's missing here. And that's what I'm going to fill in at section 4 here. Okay, until this 2, it will be the review on existing properties of GDA in Minimax. And I'm going to explain that there's some limitation. I'm going to improve it and get close to the property similar to this one. So what is this? So let's move to this. So in minimization, we are interested in minimizing a function f. And what we all know is compute the gradient and take the negative direction. And you have to choose the learning rate very well to get to the solution, right? And I think the previous applied math colloquium was about learning about the learning rate, right? So that's important. And we know it's well, but we are trying to do better. And what we know here is GD converges to minimizers. That's what we know. And have you thought about this carefully? It's somehow negative direction, so you will get to that, right? But how? And actually, in some cases, in theory these days, under assumptions, we know it will find the global solution, right? So basically, here, my question is, how can we guarantee this? There's something that we need to discuss carefully. So in a very basic machine learning class, what we learn is if you choose large learning rate, it will go diverge. If you choose small, it will be slow, but it will find the local solution, right? You have to be balanced with this. But that doesn't really explain this, right? Because it's just 1D, right? In theory, actually, finding a local minimizer is NP hard in the worst case. So if someone says, I can find local minimizer in general, that's wrong in worst case. But if we have that statement, we don't stop and we say, oh, we cannot find it, right? We still use it. We can find it, right? In what sense are we can find a gradient method? So practitioners, they still run gradient descent. Even though the landscape is very complicated, they can find the stationary point and solutions, right? So there must be some theory behind this, right? We cannot find this, but there must be some theory that we can claim that we can find the local minimizer, right? What is the theory that support that? So first thing that you learn when you learn about gradient descent, about convergence analysis, what you learn is that it converges to the station point. If you assume smoothness of the function, I think in the elementary optimization class, you learn about that fact that you converge to the station point where the gradient is 0. So this doesn't mean that it goes to the local minimizer, right? Because why? Because if you are living in the non-convex world, there is this includes local minimum points, but also include local maximum and local setup points. Can it avoid that? That should be answer to claim that GD converges to local minimum points. So we need to deal with this. So before we get to that, we are going to talk about this first. When you learn about local minimizer or local minimum, you learn about the sufficient and necessary condition, which is very elementary, right? Necessary condition, we find if GD finds a solution point that satisfies this. That's what we have just shown. There's a necessary condition. We learn that Hessian is positive semi-definite. Sufficient condition, positive definite. That's what we learn, right? And what people have found is that many practical problems satisfy the strict setup property. What I mean by that is setup points that are in practice has at least one strictly negative eigenvalue. That's the people that usually assume. So if you go back a couple of slides before, I said it's finding local minimizer and be hard. So we cannot say we can find it. But at least what's our modest goal that we can show here is that we can show that GD converges to a second order station point that satisfies this point. If strict setup point is assumed, then this is exactly the local minimum. So that's what we can show here. So we kind of restrict a little bit family assumption. That's when we can say that GD can converge to local minimum. Okay, so now the question here is, why not just focus on local minimum points that satisfy second or sufficient condition? Why not just necessary condition? Here I focus on necessary condition here, right? I use strict setup to avoid some points that is satisfied this, but that's non-optimal. But why not just start with sufficient condition and I just develop a method that only converges to that point? Would that be a problem? It depends, right? There might be a solution that doesn't satisfy sufficient condition, but that only satisfies necessary condition, right? Can anyone think about examples? Yeah.
Like x to the fourth.
X to the fourth. Yeah. Wait a minute. X. Yes. Wait a minute. Yeah, for that one, yes. Yeah, for that one. Yeah, I was thinking about this different one, but yes, that works too. So, but in more practice, what will be those things? So your answer is correct, and my idea was more towards the machine learning. So if it's over parameters the case, there's not just isolated point. There's many. It's connected. It means the Hessian. If Hessian has sufficient condition, that it means it's isolated. But in over-parameterized setting, we know that global solutions are connected. It means Hessian has zero eigenvalue. So in that case, it's important to deal with this. And thinking about other examples, there are many examples that doesn't satisfy sufficient condition, and that's important. I'm going to get to that soon, so later. So please remember that. So in GD, to show that it converges to sufficient to the local minimum, there's two things that can be stated here. I'm going to discuss about this later. So here in GD, what we know here is that GD exponentially converges to the points that satisfy the second or the sufficient condition of local minimum. That's known, and I'm going to talk about that soon. So don't worry if you cannot follow this right now. But it's very straightforward, so you'll see that. And also, another important thing that I'm going to more focus on today here is that GD almost surely converges to points that satisfy the second order necessary condition. Thinking about the previous result, I found this to be more important. And that's what I'm going to talk about today in Minimax, which was missing before. OK, so let's move on to the dynamical system. So let's view. So we have seen the gradient method that can be viewed as a dynamical system. I'm going to write dynamic system to be this, Wxk, on equivalent point x star, which means x star is Wx star is exponentially stable if spectral radius of the Jacobian of this W at x star is smaller than 1. That's if and only if. That's something it's known. And for those who are not familiar with this, I'm going to briefly review what this means. Stable means that if for each epsilon there is a delta such that for all k, this implies this. So it stays nearby. And asymptotic stable is if it is stable and also xk satisfies this. This goes to 0. And exponential stable means is that the rate is exponential. That's it. And from this, we can have this. So for the sufficient points that satisfy sufficient condition, it means we are going to show that this is satisfied for certain condition. So let's get to that. So let's view GD as a dynamical system here. So this Wxk is xk minus eta gradient fxk. Jacobian of W is identity minus eta Hessian. And saying that this spectral radius is smaller than 1 is actually equivalent to, it's very straightforward, is that the eigenvalues of this lies in an interior of the following ball. That's what you can show here. Then, if that's satisfied, GD is exponentially stable at that point. So from that, what can we conclude? If the Hessian normal of that is bounded by L, and step size is chosen, which is very straightforward, chosen with this 0 in between 0 to L over 2, GD is exponentially stable at a point satisfy the second order sufficient condition of local minimum. Why? I explained this, but I jumped a little bit onto sufficient condition. But why is that? Because the condition is saying that this is positive, definite, right? So and this means is the eigenvalues are all in this side, and this corresponds to the condition of GD being exponentially stable at that point, right? That's known. So that's why what we have here, exponentially stable at a point. So it means GD exponentially converges to that point here. That's what we know. The second statement on the dynamic system, which is more important in this talk, is that by the stable manifold theorem, which I'm not going to go into details, I'm just going to give you an illustration here, that if this, again, this is bounded by L, and step size is smaller than before, L over 1, and for any strict saddle point, any point that has negative eigenvalue, strict negative eigenvalue, if GD, what this is trying to say here is that if GD converges to a point, the probability of that being strict saddle is 0. Why? Let's look into this x squared minus y squared. And it has strict negative curvature on this side. If you initialize on this line, you will go to only this point, which is strict saddle. But if you're away from this line, it's always going to be able to escape from that. That explains this, because the line here is measure 0. And basically, the result is generalization of that. So I'm not going to go in details. So what does, so what I'm trying to say here is that if GD converges to a point, then it is almost surely not a strict saddle point. This actually gives us the statement. This, GD almost surely converges to a point satisfying the second order necessary condition without random initialization. And if we assume strict saddle, we can now say GD only converges to local minimizers, or minimizers almost surely with a random initialization, which was proven by Lee, Shumwich, Jordan, and Legg in Code, which is titled Gradient Descent Only Converges to Minimizers. This paper was, if you read it, it says that already people have found good results. It worked well in non-convex, and they proved this to support that result. And they already had this good result. That's why I think GD were working well in practice. So now let's move to the Minimax, which is the main part that I'm going to talk about here. And what I claim here, and you'll see soon here, is that Minimax doesn't have this theory. And I'm going to talk about that. So in section 4 that later, that's going to talk about our result, is that what I'm going to first say is that necessary condition was not even known in Minimax. And we're going to get to that. And given that necessary condition, we show that GDA fails to converge to points that satisfy such a necessary condition. So it's different, right? And we construct a variant of GDA that almost surely converges to this point that GDA fails to do so. So now, later I'm going to talk about this in details. Then you'll see that this is closer to the minimization, right? So we'll get to that. But before we get to that, there already exist results related to this. And I'm going to review those first and get to this section 4. And section 2 will talk about GDA and its relationship between the local minimax optimum. And section 3 will review what was known before was exponential convergence of GDA to sufficient condition. Points with the sufficient condition was known, and I'm going to review that. So as you see here, it's more about necessary condition, and it's convergence on this section 4, which is my main contribution of my work. Okay, so far so good. Okay, now let's move to this. GDA local minimax optimum. I think many of you will know what GDA is, right? Given this problem, minimax, fxy, minimize over x, maximize over y, what you do is you use GDA, right? At xk, yk, you compute gradient in terms of x, and in terms of y, you negative gradient on x, descent direction on x, and ascent direction on y. That's what you use, right? And it seems good, right? It looks good. That's why people used it. But that was the problem, right? It looks very similar, but there was subtlety that you had to be careful here. Okay, so given this, in Minimax, which optimum should we find? If you have worked on GAN, which kind of optimum do you usually look for? Anyone familiar with the Minimax?
You want a saddle point, right?
Yes, good. So I'll get to that, sorry. So I'm going to make it simple. So I'm going to introduce xy into z and saddle gradient operator to make this simple, similar to the gradient descent. I'm going to use f where there's a negative sign. So I'm going to simply write this with this. So next, yes, we usually look for the saddle point. And that's what people think to be a good one. And I agree with that. But there's something that I'm going to talk about soon. For those who are not familiar with this, saddle point is the points that satisfy this. With x star, y star, for all x, this is lower bound of this. And for other one, for any y, this is upper bound of that. That's the point that we're interested in. So it is already well known, the properties of this. Properties of this is well known. Local saddle point is in game theory is local Nash equivalent, and it's well studied. So we say local when this is satisfied in a neighborhood. That's very straightforward, right? And I think everyone will agree with this. First sort of necessary condition is the gradient is 0. Necessary condition is gradient 0, and Hessian in terms of x is positive semi-definite, and in terms of y is negative semi-definite. For sufficient condition, positive definite, negative definite. It seems pretty similar to the minimization, right? So nothing different. But of course, at some point, there will be something that makes difference, right? So let's get to that. So people use this gradient descent ascent, GDA, And let's view this as a dynamical system. And this Jacobian of W is I minus eta df. Now it's not the gradient, it's Taylor gradient operator. And what we can, in terms of dynamic system, GDA is exponentially stable as Z star if and only if spectral radius is smaller than 1, right? What does this mean? df, this, if I write this down in terms of x and y, this spectral radius of this is smaller than 1, then GDA is exponentially stable, right? Do you guys agree? It's pretty straightforward. So if eigenvalues of these are all inside this interior, this ball, then it's going to be extremely stable. Then, can we say that GDA converges to local Nash? Have you guys thought this carefully? It's already discussed in this paper. It's not that, do you guys agree? Does it only converge to local Nash or not? Yeah, with if you go back to this, now it's easier to see. Here, local Nash sufficient condition is only determined by Hessian in terms of x and y. It doesn't involve eigenvalues of entire this Jacobian of f, right? So the points that this is exponentially stable and these points that satisfy this is not, related, right? There must be the points that are satisfy both, but you cannot guarantee, right? So it can go to local Nash, but it might not go to that. So that's actually known here. But by looking at this dynamical system, you can easily see that, right? So that might be one problem why when you use GDA, you get to the wrong solution, even though you find the stationary point. Okay, so moreover, for some examples, even for GAN, Nash might not exist. That's also known. So my question here is, actually, I'm not the one who talked about this. This is the paper. Is Nash a proper optimality? Is the saddle point the point that we should look for? That's the question that this paper asks. What is local optimality in non-convex, non-concave minimax optimization? ICML in 2020. So let's look into this. So we are all in the world in non-convex, non-concave because we use neural network. Everything is complex, right? So in that case, if it's not convex, concave, changing the order makes a big difference, right? We cannot change the order. And Nash equivalent or GDA does not reflect this order, right? You guys agree? And if you look in Wasserstein-Gahn, Minimax, if you switch it, you can easily see that the meaning changes drastically. And it's not the same problem, right? Max has to be inside here because this is computing the Wasserstein distance between the distributions, right? If you switch it and find the solution, then that's not what we are looking for, right? So we need to deal with the order. So what this paper trying to say here is that we should look for the Stackelberg equivalent, which deals with the order. Why? Is this not make sense? Does it make sense? Because for x, it can only see the function that is maximized. For y, it sees the function directly, right? So that's what this Stackelberg equivalent means. There is an order here. And the thing that you have to be careful here is that it's not different. So Stackelberg equivalent deals with the order, but it includes Nash. So I'm not saying Nash is bad. Nash is good. That's included Stackelberg, but you have to deal with the larger set of the equivalent that deals with the order, because sometimes Nash might not exist. So by looking at this, we are really looking at the right solution set of this problem, right? So this is good. So what did this paper do next? They want to talk about local.
Is there a picture for the Nash not existing? Like, what's the standard picture?
Sorry, and I should have given that, but I think when I gave a talk previously, I had this, but I don't have it. But in this paper, it has some good examples. It's very simple. And with this one, they come up with just very simple GAN. If discriminator is not expressed enough to discriminate, then Nash doesn't exist. That's what they show here at that paper. Here it has a much simpler one, but I cannot remember this now, sorry. But if you look into this paper, it has very simple example.
So maybe this is not exactly an answer to your question, but if you think about the game rock, paper, scissors, of course, if you take game theory, then the Nash equilibrium strategy is to randomize and then choose one of the actions at random with equal probability. But let's say you're not allowed to do that. Let's say you must pick one action. Then there's no Nash equilibrium because rock beats scissors and so on and so forth. So there's you can maybe construct an analog with continuous inputs. So in that case, then you would not have a Nash equilibrium thing, and the dynamics, if you were to do it, then it kind of cycles around.
Thank you. Okay, so if you now agree that this might be a better solution set, larger, but better here. So now the natural thing to think about is come up with a local one. Oh, sorry, what's that thing? Somehow, this is not working. Yeah, it's fine. So this paper was the first to talk about local Stekeberg equilibrium. There were papers that discussed this in 1950, but what they claim was it's not actually the local right notion definition, and they claim that it's the first real local definition, and I agree with that. And if you look into that, you will see that. So what did they do? So it's similar than before. We want this Stekeberg equivalent, that inequality satisfied within that local neighborhood, right? That's the same thing. X star, Y star is said to be a local minimax point. That's what they use, the term they used in that paper. If there exists, this one works, but this. If there exists, so there's something slight difference that you have to look into here is that they still look into the neighborhood with the delta radius, but the maximized part, you don't maximize f, x, y for entire domain, but only within some reason, but that's is proportional to some delta, function h delta. So it's not delta. They needed this. There's some subtlety. And another thing here is that for any delta smaller than delta 0. So the one that they mentioned before in 1950-something only chose one delta. And usually in the minimization, if it satisfies local optimality in the neighborhood, it's satisfied for the smaller one, right? So they didn't need that. But for this one, they show that if it only works on the one neighborhood, it might not work in the smaller region. So they force this for any delta that's smaller than certain number. That's the difference. And that's why they say that this is real local definition here. OK, that's it. So basically, that's it. And what they show next is, the next thing to show here is necessary and sufficient condition, right? So necessary condition, first one, necessary stationary point. That makes sense. Necessary condition is this. Gradient is 0, and Hessian in terms of y is negative semi-definite. That makes sense. But for other part, it's not well specified. You will see this. Only when this is negative definite invertible, then the necessary condition was the Schur complement of df, which looks like this, is positive semi-definite. So we have this. So what I'm going to show later is I'm going to remove this. Because without this, it's pretty limited here. If I just focus on this, this is very large necessary condition that if you converge to the point that satisfies this, you have so many points that's not desirable. So that's what I'm going to talk about later. That's why I colored red. But the sufficient condition, for here it's settled because this is condition already given here. So positive, negative definite, positive definite. And they called, in this paper, they called the strict local minimax point. I'm going to use that word from now on. So in this paper, they showed the convergence on points that satisfy this sufficient condition. And as I told you before, I'm going to focus on this later. So before getting to that, I'm going to focus on this and how they were able to show that their method converges to the strict local minimax point. So does GDA exponentially converge to strict local minimax point? If you remember the minimization, this will be the first thing to answer, right? Will the GDA do that? And we already have seen, right? Plain GDA it's not easy to relate because the condition for the exponential stability is df being satisfying some property that the eigenvalue should be inside the ball. But here, even here, this is different, right? So it will not, right? That's obvious. So I'm going to talk about in section 3 about how to modify that, and then talk about non-strict, which is main focus of this talk. So, okay, so this is so-called two-timescale GDA, which was, I think, in GAN, at least in GAN, this was the first to use this, and it's called TTUR. If you're in GAN, you might have used TTUR because this is pretty much widely used one, TTUR. So it's basically this: you have different learning rate. You have larger learning rate in Y and smaller learning rate in X. So I have tau here, and tau is larger than 1, and you will easily see that here. And to make it simple, I'm going to use this notation here. I'm going to introduce this matrix lambda tau, which is just this. I'm just going to simply write this in this form. Does that make a big difference? Actually, in this paper, it only showed that this will converge to Nash under work condition. But I think the next paper that what is local optimality paper shows that this converges to strict local minimax, and that's what I'm going to talk about. So now what has changed? This is a dynamical system, but now I have lambda tau here. And what does it change? It only changed the Jacobian here. And only difference now here is that it's going to be exponentially stable when this is smaller than 1. It means this Jacobian with this matrix made one difference, right? And this goes into this point, in this ball, right? What does make a difference, right? And what the paper showed was if this Hessian is invertible, tau GDA with sufficiently large tau exponentially converges to strict local minimax points. That's what they were able to show. How can they show this? Can anyone guess? So first of all, we talk about sufficiently large tau. What happens if I choose tau to go to infinity? What happens? Right. If you know about the linear algebra, because this will be 0, 0, right? This part will have 0 eigenvalue. This part will have eigenvalue that corresponds to this, right? So what's important? So if you want to relate this to sufficient condition here, we need something related to this Hessian and this one, right? Shared complement of df, right? At least we know this. So what we need to deal with here is the ones that gets to 0. Does that have some property? And that's the main idea here. How many minutes do I have? I think.
We started 10 minutes late.
So 10. Okay, I will try to go faster. Yeah. So what did they show in the paper by them? Here is that if this is invertible, as we have seen, as tau goes large, epsilon goes to 0. So I'm going to use epsilon. So some part of the eigenvalues gets close to the eigenvalues of this, right? That's what we can see. Other one gets close to 0. But now, interestingly, they have some information of the eigenvalues of S. So it will, if this is positive, it will get close to 0, but on the direction of the positive here. So it has the information of that. So if you see here, if we are interested in the points that these are positive definite, then this part will be on this side, and this one will get close to 0, but going from this side. So when tau is large, it's going to be inside of this ball. So we can relate this to the exponential stability and the points that is satisfied sufficient condition. That's the point. So that's what they were able to show here. So now getting back to this part, drawing here. In machine learning and these modern machine learning, I think sufficient condition is important. The point that satisfies sufficient condition is important. But there are points that have non-isolated points where Hessian has zero eigenvalues, right? I believe that's important thing in Minimax, in machine learning. So, but if you get to this, existing second order necessary condition is this. This being negative semi-definite, and if this is negative definite, this is positive semi-definite. So if you work on this, only when this is satisfied we can say something. Without that we cannot do it. So we thought that this is not good enough, right? So can we come up with something that is more realistic, something that we can more complete? That's the focus of. That's what I have focused on. And this leads to the section 4, which is going to be our work. Okay, so I need to introduce one definition here, which will be new to you guys. So, which I call restricted Shor complement. It's really similar to the generalized Shor complement, but it has something here. I'm going to explain this soon. So let's say df, and I'm going to have similarity transform. I'm going to let this to be diagonal. That's what we can do, right? We can do that. So I'm just making it simple, but it works for the general df. But let's say by similarity transform, I made this to be diagonal. Then if I say this is not invertible, which is my of interest, there will be zero eigenvalues. Then there will be matrix that corresponds to these eigenvalues here. And I'm going to say this to be gamma, and U to be a matrix whose columns form on a orthogonal basis of this. But I don't think this is very important at this point here. But I'm just writing to explain what this is. So what does this being positive semi mean here? This is restricted by this U, which is not here. And this means this S, which is, I forgot the definition here, that generalized Shor complement is, with this is positive, non-negative for any V in range of U. So it's restricted. That's why I call it restricted. But let's not go into details about this. So let's focus on what we were able to show here. So this is the result that is the necessary condition. Any local minimax point satisfies this. This is known. And what we have shown here is that if H delta satisfies this. So previous definition had some H delta to be more general, but we restrict a little bit. One might say this is too restrictive or not. But previous definition, actually they never worked on this. They only care about the point that satisfies sufficient condition. We know so what I'm saying here is that we don't know which one is the best choice of the definition of the local minimax point. So anyway, if we restricted this, but I don't think this is very restrictive. It just say H delta is this, right? It's not restrictive. And independently, some other authors call this to be local optimal. It was independent. They came up with this. But anyway, if I assume this, then we can come up with some good necessary condition where S restrictive is positive semi-definite. And that was the starting point here. By having good necessary condition, we were able to show almost Shor convergence from here. So what is different here? So I'm not assuming this is invertible. I still need S restrictive to be invertible. I think that's something that I have to remove it. But at least I can work on this being invertible, but this being not invertible. So I think it's a progress. under this, we were able to come up with this result, where this eigenvalues of this satisfy these three. These two are the same as before. Uj is eigenvalues of this, uj are this. So now you see that this part is related to the necessary condition, right? But we have this. What does this mean? And can anyone guess what might this be meaning here? What is this? So it's the singular values of gamma. If you have this one, if you relate this to the necessary condition, this has nothing to do with the necessary condition of the optimality. It's just what you see here is this. If, let's say, we are dealing with the points that satisfy necessary condition, eigenvalues of this is positive, and this is positive, then everything will be here. What about this? It is not related to the necessary condition, but it's just coming from here, outside, might be. So it's just making unstable, and it's related to something like saying Minimax. People say if you run Minimax, it's unstable or it goes to the limit cycle, right? If you see here, this lambda j is this is imagery, right? Usually in dynamical system, when you have I something, it means it's rotating, right? This tells something about that the method can be unstable, even with something that we have here. So anyway, that's what we were able to show. Sorry that I think I have 4 or 5 minutes. So with this one, even it's satisfied, everything's on this are inside here, but this can be outside. So what we were able to show here is that tau GDA for any tau, even for some non-strict local minimax points, because of this, it can be unstable. That's, I think, what we're seeing in reality if you run tau GDA. So I think having this, I think it explains it theoretically why existing method might be not working well. So what do we do? How can we improve this? Is it something that we cannot do? Because GDA is the only thing that we can work on. We cannot deal with this. Anyone? What can we do here? There's 2 things that I'm going to talk about today. And that will be only thing here. And I can explain it from here.
Yes, one thing you can do is push it to the side.
Yes. Yeah, push this here. Or make this larger. And I'm going to talk about both of them. So extra gradient is the one that people use a lot to show convergence in Minimax. For convex concave, even for convex concave, GDA doesn't converge to the solution. And EG is known to have a better convergence. And people use this to prove it. And I'm going to use this in terms of dynamical system. And if I look this into the dynamical system, this being exponentially stable means eigenvalues of this lie inside this. So the one thing, enlarge this. Because I want this part here. Right? That's what we did. So what we were able to show here is that if you use tau EG, 2-timescale EG, we were able to make this work better. But what's the problem? Actually, there also is a case where it still is outside here. There are no method that can cover this because there's no method that can have this whole reason. Because I don't think there is any method there existing. So anyway, this was progress, but there was something still missing here. And our goal was to, if you remember the minimization, our goal is to show that construct a variant of GDA that almost surely converges to a second order station point. It means a point that satisfies the necessary condition, these. To talk about that, if you go back to the minimization, they had something similar, something as strict saddle. And I had to define this. I call this strict non-minimax point, where either this, at least this and this at least has one strict negative eigenvalue where it can escape. That's what I did show. So it's basically the same here. as before by the stable manifold theorem under some condition on the step size and the Hessian. If Z star is strict non-minimax point, previously it was strict saddle, then we were able to show that probability of limit being this is 0. Similar, right? Still, there's some assumptions, but I think this is the first work that we're able to show something that is similar to the gradient descent. But still, I said there is something here, and one already answered. But for me, it took a year to figure out, because I thought there was no hope to figure this out. But then, this will be the last. I wanted to move this. But I don't want to change the properties of this. Because if I change it, but also I change this, then everything is lost, right? We have to change this, but maintaining this. And since I have no more minutes, so I'll just go over this correctly. So this is related to the eigenvalues of this. We can look into that. So no, most of people do this, fix this by putting regularization on y, and many have done that. But I didn't want to do that because it will change the station point. I wanted to figure out implicit regularization that doesn't change the station point, but while this, we can move this towards inside this. And I knew that there is alternative method. That this is alternating method. You update xk plus 1 first, and then update this. That's this. People in practice, people use this, but in theory, people didn't use this much. But I thought if you run this simultaneous method and this one in bilinear, we see that both doesn't converge to the solution, but you will see that this is stable. And I remember that, and I thought this might help. And I started with this alternative operator, which includes compute y graded not at x, but after you update something here. So what I did was, if I choose gamma inside here to be scared with tau, so if I choose this arbitrary, it didn't work. If I choose this to be scared with tau, so this 2-timescale and this one is different. So we need to be careful with this. But eventually, we were able to show that with this, we were able to shift it inside this pinner-shaped region so that we can have this complete theory here. Thanks for listening. So conclusion is, we established the more complete second-order necessary condition that we were able to work on. This didn't exist. I was surprised because in Minimax, people were not looking careful. They looked more Nash equivalent or saddle point, but this wasn't existing. That was the difference with the gradient descent. And we were able to show that existing method doesn't converge to that point. And we showed that this new method can converge, almost surely converge to local minimax optima. That existing method, the tau GDA, almost surely escapes. So that was it. So I think this is pretty closer to the theory that we have for the GD, and this might help better when we do minimax optimization. That's the hope. And my open question for me is, will there be a gradient method that can converge the global solution of the GAN? And if that happens, will it be really different from diffusion model? I don't know, but that's what I'm interested in. Thank you for listening. Thank you.